Okay, this video is going to be a really quick video on essentially mimicking the Hex Dump command in Linux. So I have a text file here, hello.txt, and we have some text in this file. Each one of these characters is an English character, and by default it's represented as ASCII. The ASCII code is an acronym that stands for the American Standard Code for Information Interchange. It's basically a mapping from a numeric value to an actual character. All right, so here's the Ascii table. Hopefully you've seen this before. And you have some number, and the first 32 are kind of characters that we're not necessarily familiar with. They are control characters. A couple of them we are, like a new line character that actually tells the text editor or the terminal to move to the next line. The carriage return, the tab. The tab is represented by text editors as 8 spaces, but it's really just stored as one character. So all of these are stored in the same number of bytes. There are the highest number is 127, and if you include the number 0, that's 128 different ASCII characters. All right, so that means there are 128 different ASCII characters. That is 2 to the 7th. That means in 7 bits of information, we can represent all of these different symbols. All right. So when I look in my text file here, I have my text editor Adam open up, and hello.txt. This character H could be stored in 7 bits of information, but the sort of common chunk of information used in computer science is 8 bits. So the 7 bits of information can fit in 8 bits. We just add a 0 in front, right? And so that capital H character has a value, a quantity that's actually stored in the computer as 72, right? And then the hexadecimal value of that is 48, right? So there's a command, Hex Dump, Hex Dump -C, that allows us to look at the information in the file as if it were binary data. Now it actually uses hexadecimal, hence the name Hex Dump, but every digit of hexadecimal can be represented as 4 bits. Right? So here we see 4 and 8. That would be 8 bits. So every 2 digits of hexadecimal is 1 byte of information. And so in hexadecimal, the number 48, if we look to our ASCII chart here, 48 is the letter H. Then the next byte of information is 65. So 65, now this is hexadecimal, remember. So, in this chart, this first column is the decimal value. These two values, these two quantities represent the same quantity. Right? It's just different ways of representing what that quantity is. So these are different number systems, but it's still the same amount of things, right? So we want 65 in ASCII. So that is the lowercase letter e, 65. So we had 48 and then 65. That's HE, right? 48 and 65. And then over here on the right, the hex dump command, tries to map out what characters you're using. Right, so if we look back at our text file, we see HE, right? That's correct. We see 2 of the same character, right? So if we look in the bytes, we should see the same byte. And sure enough, we do, 6C. So that should be, 6C should be lowercase l in hexadecimal, and it is. All right, so this is just sort of verifying, what the hex dump command is doing. One other thing it does is we have this dot here, right? Because of the way it lays out the bytes, there's not always a printable character for the particular byte. So for example, in our file here, there is a new line character directly after the cursor. That's what tells the computer to go to the next line. It tells the text editor you're supposed to start printing on the next line. That's specifically what a new line character is for. And it's stored just like any other character. Okay, but that character isn't really printable in the sense that it's a control character. It controls the action of the display. So it controls the action of the terminal. Move the cursor down here. There's not actually one symbol to represent what that is. What it is an action, right? So to represent an action character or a control character or anything that isn't displayable, right, the command replaces that with just a dot. All right, so here we have HELLO, comma, space, and then WORLD, exclamation point, and then here is that dot, that control character. So it doesn't know how to represent this as one symbol because you can't really. So let's look up OA in hexadecimal and see what that is. So it starts with an O, so a 0, so that's something in this range, OA, so this would be 0A, and that's a line feed. That's also called a new line character, right? So it has no single symbol visual display. It's a control character. It's an action, right? So all of these are control characters, and we're not usually that familiar with a lot of these. Some of them we might be the new line character in the tab, for example. All right. So this is kind of what we want to mimic. We're going to make a quick little Python program that reads data from a file in binary form and reads it 1 byte at a time. And then we're going to change the format of this layout. We're going to print out 1 character per line, but on each line we're going to print it out kind of like this Ascii table where you have the decimal value and the hexadecimal value, and then we're going to have a binary value, and then if there is a character display, we're going to use the character display. Alright, so let's get started here. Let's call this byte dump because it's more than just hexadecimal. So new file, byte dump.py. Alright, and so one of the first things we want to do is we want to open a file. So most of the time in Python, when we open a file for reading or writing, we're dealing with text files the vast majority of the time. So when you do that, you use the open function, and you open the file by the file name. So we're going to open hello.txt, and if it was just a text file, which this is, you could open it with the R flag for reading, and we're just going to read in the data as a string. And far and away, that's the most likely scenario you're going to be working with. But in this case, we actually want to look at the binary data. Okay, so we're going to use we're reading the data in, but also we're reading it in as binary. Okay, so that little B after the R is important. So we're going to open this file for reading in binary data. Alright, so we have this file open. We need to decide how many bytes we want to read in at a time. Right, so this is our chunk size. We have a chunk size, and we just want to read it in 1 byte at a time. Okay, that's all we're going to do. So to do this, we're going to need to create a loop and iterate through that loop, and each time through the loop we're going to get 1 byte of information from the file, and then convert it to the different forms, the different representations that number represents, right? We're going to convert it to decimal, we're going to convert it to hexadecimal, to binary, and then also we'll get the ASCII representation if one exists, right? Okay, so to do that we need this loop. We're going to say while and then true. And we're going to get a byte of information. So a byte is going to equal our file, f, and .read. How much are we going to read in? Well, we're going to read in our chunk size. All right. And then the last thing to kind of, this is an infinite loop, right? When you have a condition here, this condition tells you, Python checks this condition to see if we should keep running the loop. Well, if this is true, it keeps running. So since we have a literal value of true typed in, this is never going to break unless we use our special break keyword. All right. So when do we want to break out of this loop? Well, so if we don't have a byte, so if the byte does not exist, right, or the Boolean representation of the byte is equivalent to false, then we're going to break. Right? So this will break us out of the loop whenever we try to read 1 byte of information and get no value there. Okay? And just to see what kind of data this is that we're getting back here, we're kind of used to the primitive types of data, a string, integer, floating point decimal, booleans. Those are kind of the standard ones. This is actually a special primitive type as well in Python. It kind of represented strangely in a literal format, but let's just print out the type of this information. So print out the type of our byte, right? Just to see what it is. So this loop should run for every single character. It's going to print out the type, right? And then so that should be a lot of the same thing printed out. And then eventually, after each one of these characters, right? So it should be around 30, 40 characters, something like that. It will break out of the loop because it should encounter this byte value trying to read in a value, and there's nothing there. So the Boolean representation of that would be false, and so if not false would be true, and then you break out of the loop. All right, so let's try this Python 3, and we're going to call this byte dump. Right. So this is a bytes object. Okay, so it's not a string, it's not an integer. Right? This is a built-in type to Python. Okay, so we're not going to talk too much about that. We're just going to use the built-in functions of Python to convert it to the appropriate representations. Okay, so we'll move this line down a little bit, and so right away, if we're trying to read the byte first, and immediately if we read the byte and there's nothing there, we break out of the loop. Then our program's finished. Now, if we read the byte and there is something there, then we need to convert it to a few forms, right? So first one we might want to convert to is the decimal version, right? So we're going to use the ORD command, which stands for ordinal, and that function, when you give it a byte or a string, will convert that value into the decimal representation of that. So it'll convert it to an int essentially. So we pass in byte here, and we can print out decimal. And now we can run this and see we should get a little different output. And now we see all of these values, right? Okay, so the first one we see is 72. All right, so 72, if we look up here, first character is capital H, so let's look at our Ascii table, and capital H, the decimal value is 72. Okay, what about the next one? 101. Okay, well, we know the second letter is E, so this should probably be 101 in decimal. Sure enough. Now this is just, again, this is the decimal representation, right? Hexadecimal 65 is the exact same quantity as decimal 101. These two numbers are representing the same number of objects. It's just a different way to represent that number. All right, so we're gonna convert to a few different number systems here. So we've got the decimal value. We're going to need the binary value, right? So we can use the built-in bin function, and we can pass in our decimal number, right? So let's print out the binary value. Binary. Okay, and the result of the bin function is the binary representation, but it's as a string. Anytime in Python when you have a literal value typed like this, with no prefix, it's considered decimal, right? So to return a value in binary, it would just get stored as decimal otherwise, right? So this actually returns a string, and you're going to see that when we print this out, all of these values start with OB, okay? And these are actually string values returned from the bin function. We can, prove that with type. What type of data are we getting back from the bin function? Let's save that and run it. Right, it's class string. Right, but we can convert that to an integer. So you can just pass in the string OB, and that would convert to an integer. I believe base 10. Oh, you have to pass in the base, I believe. I think. Might have to move past this because, yeah, there. So I passed in the string value and then the base, right? And so if I get rid of the type, I think this should be the same value, right? So we converted it to a binary string, binary representation of the value as a string, and then convert it back to an int, right? That's really neither here nor there, but that's just kind of to show you that you can. All right, so we have decimal, and we have a binary representation. All right, and we don't really want to see this OB at the beginning, right? We just want to look at the binary digits, right? So what we want to do here probably is we have this binary value, but we want to take a slice, and we want to start at the second character and go, you know, the space after the second character and go all the way to the end. You know, think of it like a slice of bread. The first slice would be before the beginning character, right there. The second slice, or I'm sorry, the 0 slice is here, the first slice is there, and then this is the second slice. And we're going to take the second slice to the end. And that's what we're going to store in binary, in the variable binary. We run that, and we see that gets rid of the 0b. All right, so that's pretty good here. We can also, we don't need this type byte anymore, that was just for demonstration purposes. But we want to check to see if this is a displayable character, and if it is, we might want to have the string value for it. So if decimal, what are our displayable characters? We need to check to see if that value is between some range of our displayable characters. So our displayable characters kind of start out here. You know, it's up for debate whether or not space is displayable, right? So if the decimal value is between like equal or greater than 32, and then equal or less than or equal to 126, right? These are all displayable characters. I can actually print a character as the value. And then the delete, this is an extra control character that we can't really represent with the symbol. Okay, so we want to check between 32 and 126 inclusive. All right, so if decimal is greater than or equal to 32, and also decimal is less than or equal to 126, that means it's in our range of computable values, right? Or representable values, right? The values that we can represent with a single symbol. So we'll have this symbol, and we'll start the value out as not display or no display, right? And we'll print this out if it's a non-display character, right? But if it's in this range, it is a display character. Okay, so in this case, if our decimal value of this byte is between this range, then we can convert the decimal value to the character version, the ASCII version of this. So we can pass in decimal here, right? When we get that symbol, and so down here we would have symbol. Right. Now we're going to clean this up eventually, right? This is kind of, it would be nice to have them all, you know, matching the starting points here and not offset and not jagged. So we'll fix that up too. But let's go ahead and see what we have first. And so here we go. We have HELLO, comma, space, world, exclamation point. New line character has no display. Then we have bytes, right? And then we have an additional new line character at the end. Right, so this looks like it's working pretty well. The last thing we want is the hexadecimal value, right? So we need some hexadecimal value. So hexadecimal is base 16, and just like the bin function, there's a hex function, and I can pass in that decimal number and get a hexadecimal string. Now remember, the binary string had an O or a 0B in front of it. So for hexadecimal, there's a 0x, right? And that, whenever you see the 0x, that stands for hexadecimal. 0B stands for binary. All right, so 0x is what we're going to see here. We can do the decimal value, then we'll do hexadecimal, and then we'll do binary. Right, and here we see the OX. So this is common format you might see, especially when you're talking about memory locations or something like that. Those are usually represented in hexadecimal because they're really just binary addresses. But hexadecimal is just binary. It's just a more compact format of binary, right? Every 2 hexadecimal digits represents 8 bits. And it represents 8 here, even though there's just 7, but there's an implied 0 at the beginning, right? So 0, 1, 1, 1 is 7 in binary, so that's the 7. And then 1, 0, 0, 1 is 9 in hexadecimal. I think I misspoke there. Is 9 in hexadecimal, and that's 9 in binary, right? So we're pretty close to being finished. We just need to kind of clean this up a little bit. And what we want to do here is... do we want to start with decimal? Yeah, so we're going to have the print version of decimal, and we're gonna make decimal a string, right? And we want all of these to line up on the right hand side, and if there's any extra space, we're just going to add a blank space to the left. Okay, so we're going to have a window. What's the biggest character? How many digits is our biggest character? It goes up to 126, 127, so there's only 3. So that's our window size, and we want to justify our content here. So this value here is going to be a string. It's either going to be 2 characters or 3 characters, right? So what we're going to do is format this so every single one of these is 3 characters, but if our actual data is 2 characters, we want to add a space at the beginning. So that would essentially justify our data and add a space on the left. Right? So we can use the .rjust function, and this right justifies whatever string data you have. This has to be string data on the left. It'll right justify it. It'll justify it to a given window of characters. So we want to justify it within a 3-character window because we have data that's either 3 characters or 2 characters. Right? And so we want all of this stuff to be right justified. And then what character do we want to use to pad the left if our data is smaller than our window? So our data here is either 2 or 3 characters. Our window is 3. So if it's 2 characters, what character do we want to put on the left? So we're going to just put a space. Right? And so then here we can put our print version of decimal right there, and we can see if that lines up. And see what that's done. We have a 3-character window here, right? And we justify the data to the right-hand side of that window. And what character do we use to fill in the rest? A blank space. Okay, so these are the decimal characters. Also for hexadecimal, we probably want to strip off that OX, right? So let's do that as well, just like we did in binary. See, we stripped off the 0B. So to do that, we'll take the slice and go from the second slice to the end. I'll run this again, and all those 0x's should be gone. But now we want to, if we have this A character, there's an implied 0 at the beginning. Right? This is actually 0A as far as the entire byte is concerned. We want to show that, so we're going to want to right justify this as well. So we're going to have p hex. That's going to equal hexadecimal should already be a string, right? Because the hex function returns a string. So we will say hexadecimal. We want to right justify that in a window. That window of characters is going to be 2. And instead of an empty space on the left, we want a 0. Okay, so with the decimal value, we didn't put a 0 here. We could have, right? But we're decimal values, we're not used to seeing zeros in front. With hex, we kind of are. So we're going to put a 0 in front of hex. Oops. and then now we're going to use p-hex there instead of hexadecimal. So that's the print version of the hexadecimal number, and now we see 0A. We've added a 0 in there. Right, so this first column is the decimal value, this is the hexadecimal value, and we need to do the same with binary. Binary should be a string, so this is the print version of binary. We're going to take the binary number, we're going to justify it, right? And these binary numbers should be 8 bits, right? Some of them are shorter, right? But we want to pad zeros at the beginning, just like we did with the hex. So the window of characters, there should be 8. Right? We want to pad all of our data to the right in a window of 8 characters, and then use the 0 characters to pad to the left. So to see if this is true, this comma character should have 2 zeros, like starting from the right, 2 zeros, 2 ones, 0, 1, and then another 0 here when we run this again. So the 0 should show up on the left. Should save that. All right, and where's our comma? There. Wait a minute. Binary. Oh, I'm still printing out the old version. So we need to print out the print version of binary in order to see any changes. All right, and now we see they're all the same width. Right? And here's the comma. We had 2 zeros, 2 ones, 0, 1, and then we actually needed 2 more zeros, right? And so it put 2 more zeros in front. So that looks like it's working. And then the last part is the character. And you could add some more spaces, whatever you want to do, but now at least everything kind of lines up and you can look at the differences. It's not perfect visually, right? But you want to provide, it's a better user experience, so we did the justify. And so you can do that. Right, so this is a nice little version of Hex Dump, but it provides a little bit more information. Gives you the decimal, the hexadecimal, and the binary, and the character version. And instead of displaying a dot, if there is a non-displayable character, it says no display. So in a lot of ways, it's a little bit more useful. But it's just taking a byte of data at a time of a file and printing it out. Now I do want to show one more thing. I have this picture here. This is binary data. And it's a PNG image. So there's no guarantee that the data in a file is text data. But what this program does is it assumes that we do have text data. And so it's printing things out as if it's text data. And it makes sense for a text file. But I'll show you what happens when we do this for a binary file that's not text-based. There are some fields, some bytes in here that are text, and they're meant to be text, but not the entire file. And you'll see that it'll just be kind of gibberish over here. So we can type hex dump -C and use our file. This is our image, right? And you see it's a pretty large file, and over here, this is the gibberish that we get back, right? This isn't actually meant to be text. It just happens to be the same byte value as a character. And so this program is converting it to a character, right? But it's not actually meant to be a character. It doesn't really represent a character. You can make any number into a character, but that doesn't necessarily give it meaning, right? So the meaning of this file is derived by the protocol and how the information is divided up in the file. Now here at the very top, we do see there are some characters that are meant to be characters, right? Text software, genome screenshot, that sort of stuff. This is definitely meant to be character data. It would be very unusual for this to happen randomly, right? To just have English characters based on random bytes of information appear that are readable, right? Extraordinarily unlikely, right? So this is meant to be bytes of information, right? But the rest of this stuff is not. But our program can still try to do it. It just doesn't make any sense to do that, right? So we can run our program too on this, and it's going to be even longer output because we have 1 byte per line, and they're doing 16 bytes per line. But that's okay. We can still run it. Python 3. It's always fun to see how much work we can make the computers do, right? Non-UTF code string. Okay, so Python doesn't like this. Python recognizes that this the bytes of information are not in UTF format. Okay, so we'll just skip that part. But essentially, we would get something like the byte of information, the binary version, and then some character. And I'll have to look into why that is. There's a lot of encoding issues that pop up all the time. There's syntax error, file on line 1, no encoding declared. So when we're trying to read the file, it seems like it wants an encoding declared, and it didn't need it for the other files. So that's something we can look into. That's not particularly important, but you could make it so that your program attempts to do what Python or the hex dump command does here as well. All right, so that's all we have for this particular example. We're taking bytes of information, we're converting them to their decimal value, their binary value, their hexadecimal, and we are converting it to its symbol representation as far as Ascii is concerned. And remember, Ascii is just a mapping. American Standard Code for Information Interchange. It's just a mapping from one character, or from one number to a character. So this doesn't really do anything. It's just a standard. It's a protocol that we agree on, right? And if we're using it, it makes sense, right? If our file is using Ascii, the output will make sense. This file is not using Ascii, so the output does not make sense. So we have to agree on what protocols we're using for any data to make sense. All right? So that's all we have for this video.